In section 9.3, we're building off of the absolute value equations that we've been introduced to in section 9.2. Now we're going to work with inequalities instead of equations. So we're going to be working with two major cases. Case number one is going to be absolute value expressions that are less than a number, or less than or equal. So this works for the less than, strict less than, and it also works for the less than or equal to. Same approach, same kind of case. Case number two, as you might have guessed, is when we have an absolute value quantity that is greater than a number or greater than or equal to a number. So we'll have a method for dealing with case number one and a method for dealing with case number two. We've already talked about how to solve absolute value equations when we are setting things just equal to a number. That was in section 9.2. We're going to build off of this idea. We're going to take the example that I started out with in 9.2, where we had the absolute value of x equaled 3. And we were able to rewrite this as x equals 3 or x equals negative 3. And when we plotted it on our number line, we had a point at negative 3 and we had a point at positive 3. And those were the solutions to this equation. Well, by taking our equation and turning it into an inequality, we're going to have, instead of two fixed solutions, we're now going to have several solutions. These solutions are going to be more than one value because we're saying we want numbers that are less than, not exactly equal to, but less than. So let's see how we can rewrite this. Okay? We want to find values for x that are less than 3. Or I should say absolute values that are less than 3. So we could say that, well, numbers that are less than 3 certainly work, don't they? So if I were to put the number 2 in here, positive 2, and take the absolute value of 2, well, 2 is less than 3. So we could start by drawing our number line here at the numbers that are less than 3. And because we're not allowing for equality in this system, we have to say that 3 is not a solution, so we have to put a border around it. And then we're looking at all of the numbers that are lower than 3. But is this the solution to our inequality? No, it's not. Why isn't it? Because as soon as I put negative 4 in here, and I ask, is this true, right? Is this true? When I take the absolute value of negative 4, I get positive 4. Is positive 4 less than 3? No, it's not. So I'm bound on my left-hand side by numbers that are bigger than negative 3. So I have this interval here. And now I just have to combine these intervals in a way that makes sense. So all the numbers that are between negative 3 and positive 3 satisfy this inequality. So how can we sort of generalize this example? Because this works every time. What we'll say is that we can rewrite this inequality, and I'll even turn it into letters. When we have an absolute value quantity that's less than a positive number, right? Because if it's less than a negative number, we know we don't have a solution. Absolute value only gets us positive numbers. But that doesn't mean we only are allowed to put positive numbers inside our absolute value function. In fact, we're allowed to put any number we want inside there. But it will always return a positive number. So we can rewrite this as saying x must be less than a, and, not or, but and, x must be greater than negative a. And we sort of demonstrated why this is true when we used an actual number. And we saw that, oh, we could put positive whole numbers in there, or any number that was between 0 and 3, and it satisfied the first part of our absolute value function. But we couldn't keep going past negative 3 because our absolute value function turns those negative numbers into positive numbers. And those numbers eventually get bigger than what we set our original inequality equal to. So another convenient way, and I think a more useful way of writing this. I mean, you could split this into two separate inequalities and solve for x in both cases. But we can rewrite this according to what we learned in section 9.1 as a compound inequality. So x is, and you can kind of see how we do this on the number line. Remember, our solutions were between negative 3 and positive 3. They were in this interval right here, right? And so whenever we've got a solution set that's between two numbers, we can write it as a compound inequality. So we could say our solutions are from negative a is less than x is between, so our solution set is x is between negative a and positive a, all right? So this is another way of rewriting this, this inequality. When we're dealing with less than or equal to, we can always rewrite it as x is between negative a and positive a. Okay, this is case number 1. So let's take another example of this and work with it, just so we get a little bit more comfortable with it, and we'll make our example just a little bit more difficult. Let's say we've got the quantity 3x plus 1 divided by 2, and we'll say that it's less than or equal to 10, just to be on the safe side. And actually, let's take one more step, and we're gonna add 5 to it, and we're going to say that it's 15. Okay. So the strategy for these is we've been working with the case where all that's on one side of our inequality is the absolute value function and whatever's inside of it, and then everything else is on the other side. We're going to use that same approach. And that's how you solve these, is that you isolate your absolute value function first and then apply the rules of the absolute value function depending on your inequality. So here, I would subtract 5 from both sides. And now I've isolated my inequality, or my absolute value. It's all by itself. In this case, I don't have to flip the sign because I'm not multiplying or dividing by a negative. Remember, those are the only two exceptions when working with inequalities. Here I just subtracted 5 from both sides, and I get something in the form that I can now work with. And we said we're going to use the rule that, you know, the absolute value of whatever's inside there, when it's less than or equal to a, we can rewrite it as the same quantity sitting between positive a and negative a. Okay? So we're just going to rewrite it in that sense. So negative 10 will be on the left, and we keep our signs facing the same direction. And now we can drop our absolute value sign. And we get our absolute value quantity is between negative 10 and 10. Now we just need to solve for x. Solving a compound inequality, just like we did in 9.1, we just have to do everything to all sides. So whatever I do to the middle, I have to do to the ends. Whatever I do to the left-hand side, I have to do to the other two sides. In this case, I want to eliminate the fraction. So I'm going to multiply everything by 2. When I do, I get negative 20 is less than or equal to 3x plus 1 is less than or equal to positive 20. Now, subtracting 1, I have to subtract 1 everywhere, and I get negative 21 is less than or equal to 3x, less than or equal to 19. And now, to get x all by itself, I divide everything by 3. And I get negative 7 is less than x is less than the very cumbersome fraction of primes, 19 divided by 3. If I were to plot this solution on a number line, which often your instructor will require that you do, I get to make my number line very convenient. So let's see. I know that this is a number that's a little bit bigger than 6, so I'll put it over here. And I'll say that that's 19.3, or 19 divided by 3, sorry. And then over here I have negative 7. Now I have to determine whether or not I need to include the numbers that are my boundaries. Well, I get to in this case because equality has been allowed in this system. So the way that we would mark that is that we would fill in our boundaries on this side. And now we just need all of the numbers that sit between those two boundaries. So we would mark this entire interval. This is the number line visualization of our solution set. But when we were working with compound inequalities in 9.1, there were other ways that we could describe this. We had set builder notation and we had interval notation. So let's go over how to write this visual representation in those two forms. So set builder notation is going to be the easiest one, because what we'll do is we'll just build our curly bracket. Our solution is the set of all x such that x is between negative 7 and 19 over 3. This is why I like set builder notation, is that you don't really have to do too much more work to it. So this is the set builder notation for the solution set of our inequality. So this is set builder, and then we also have interval notation. Interval notation is easy to see from the number line. Our interval goes from negative 7 all the way to 19 over 3. And we're including our boundaries of our interval. The way that we indicate that is by using square brackets. In this case, we're including both boundaries, so we use square brackets on both sides. And then we move from smallest number to biggest number. Our smallest number goes on the left, and our bigger number goes on the right. Those are the visual representations of our solution set for this inequality. All right? Using this strategy, when you start out with absolute value quantities that are set less than or equal to a value, you will always get an interval solution that's just one interval. You'll always get, kind of like what we talked about, solutions that rest between two boundaries. Okay, this will always be the case. It'll always be something like that. So right out of the gate, when you're dealing with inequalities, check which way your inequality sign is facing you. If it's facing to the left, if you're dealing with a less than, then right away you can kind of expect a certain solution shape. You know, it's going to be one interval, and it's going to be between two things. So, you know, as you work more and more with these inequalities, you get an idea of what to look for. And particularly when you're taking a test or a quiz, you know, this saves you a lot of time if you can remember, I know that I'm going to just make this transformation right here. I have this quantity is less than a, well, okay, I'll just rewrite it as that and solve for x. Okay. Case number 2 is when we have an absolute value quantity for x that's greater than, or it's greater than or equal to, a value, which we're calling a. So the method that we approach is similar but not exact to the way that we approach our first case. In our first case, remember, the way that we got to x is between negative a and a was to rewrite our original version as x is less than a and x is greater than negative a. And we demonstrated this on the number line to prove that this is true. And then we rewrote this expression with the and as a compound inequality, where we could then put x between negative a and a. For case 2, we can rewrite our inequality in this form. We have the absolute value of x is greater than a. We can rewrite as the absolute value of, we can now drop the absolute value signs and say that x is greater than positive a, or x is less than negative a. So let's take a really basic example, and we're going to put a number in here, and we'll prove why this is true, right? Or I should say demonstrate why this is true. So let's take the absolute value quantity x, and it's greater than 3. All right? 3 has been our number today. So what numbers satisfy this inequality? Well, clearly numbers, positive numbers that are greater than 3, when I put them in here, like the absolute value of 4 is greater than 3, well, that's clearly 4, and 4 is clearly greater than 3, so that's right. On the number line, I would express this as numbers that are greater than 3 satisfy the first half of my inequality. I can't include 3 in my solution set because I have a strict inequality. It's not greater than or equal to. So all numbers that are greater than 3 but not 3 are part of my solution here. And the way that I visualize this on the number line, or illustrate this on the number line, is to shade in the interval that is greater than 3, but then close off the point around 3. But with our absolute value function, if I put, for instance, negative 4 in here, greater than 3, I know that the virtue of my absolute value function is that it takes whatever's inside of it and turns it into a positive number. So if negative 4 is inside my absolute value, that means that I have 4, positive 4, once my function is complete. And again, 4 is greater than 3. So not only are positive values that are greater than 3 part of my solution set, but also negative numbers that are less than negative 3. So if I have the point negative 3, again, for the same reasons, I can't include negative 3 because I don't have an equality here. So I have to indicate that by circling the point around 3. But all of those numbers that are less than negative 3, like negative 4, negative 5, all the way out to negative infinity, those numbers are also part of my solution set. So I have this number, or this set of numbers, or this set of numbers. Here's where we get our difference. It's not the numbers that are between negative 3 and 3. It's the numbers that are on either side. That satisfies our inequality. So this is the method that we'll use to solve inequalities where we're dealing with a greater than sign or a greater than or equal to. And let me write that on the board so we have it. Just so we have it. So we can rewrite a case number 2. We can't write it as a compound inequality because that's not going to help us. But we have to write it as 2 separate inequalities. The first one being that x is greater than positive a, or x is less than negative a. Okay? If it helps you to think about a looking glass from Alice in Wonderland, that's how I like to think of it. I noticed that I have, with absolute value, in our previous case, we had a mirror representation of the things that were going on. What was true on this side was also mirrored on our negative side, right? So what we do in this situation is that we keep the side that we start with. In order to drop the absolute value signs, we keep our greater than sign, we keep our positive a, right? This gets us the first half of our inequality. But then we have to go through the looking glass. And when we do, not only do we flip the sign of our value, but we also flip the direction of our inequality. And that will give us the second half of our solution set. So let's take a rudimentary example. X plus 3, absolute value of x plus 3. And let's just make it a little bit more complicated. And let's say that it is greater than, I'll use a negative 2 here. All right? Now, right off the bat, you might see this negative number on the right-hand side and go, oh, the solution set does not exist, or it's the empty set, right? Because when we set an absolute value quantity equal to a negative number, we don't get any number out of that absolute value function that satisfies that equality. Well, we have an inequality here, and we're not done isolating our absolute value. When we do isolate our absolute value quantity, we actually end up with a positive number on this side. So I wanted to set up this example just to illustrate that, like, beware. You might see a negative number on the right-hand side and immediately go, oh, there's no solution set. Well, no, in this case, we've got to work through it. When we do, oh, negative 2 plus 7 gets us a positive number. So this can be true. All right? This will have a solution set. So we're going to use the approach that we just talked about. We're going to rewrite our absolute value quantity and rewrite, I should say we're going to rewrite this as two separate inequalities and solve both inequalities for x. So the first one being x plus 3 is greater than 5. And then we have to go through the looking glass. X plus 3 is less than negative 5. Those are our two inequalities. So solving for x, we subtract 3 from both sides, and we get x is greater than 2. Subtracting 3 from our second inequality, we get x is less than negative 8. So let's illustrate these solutions, or these solution sets, on our number line. Where we have x is greater than negative 2, so I come out to 2. And again, inequality, it's a strict inequality, which means we can't circle our point, or fill in our point, we have to circle it. So all these numbers that are greater than 2 satisfy the first half of our inequality. Now we have to go and visualize our other set. So I'm just going to call negative 8 out there. And then all the numbers that are less than that are to the left. This is our number line representation of our solution set. Your instructor is likely going to ask that you express your solution as either a set builder notation solution or an interval notation solution. So let's write those alternative versions. The set builder notation is the set of all x such that x is greater than 2 or x is less than negative 8. There's your solution. And remember, it's not and, it's or. Your interval notation solution, we can find that rather quickly by looking at our number line. So we have two intervals here, don't we? We have two shaded regions. So we're going to have two interval notations. And like in section 9.1, when we were dealing with compound inequalities, we're going to use our union set symbol to visualize or to write our solution. The first interval, we always start with our lowest interval. We always go from low to high. So, and then we have negative infinity out here. That's the lowest it goes. Positive infinity out here. So whenever we're dealing with negative and positive infinity, we exclude them. So we say that our first interval goes from negative infinity, and then it comes up all the way up to negative 8, but we cannot include it, right? This is what that circle representation means. You also see notation like this, where we've got a parenthesis around 8, and then all the things that are to the left of it. So this notation is also helpful because you know what symbol to use for your interval notation but I was always got in the habit of writing a circle around it. So this interval goes from negative infinity to negative 8. And then because we're saying it's or, we have to use our interval notation set union, which means or. So it's the interval from negative infinity to negative 8, or numbers that are on the interval from 2 to positive infinity. And those are the solutions. So again, just to sum up, with absolute value inequalities, we have two cases. We have cases where the absolute value quantity is less than A, or it could be less than or equal to. In either one, we rewrite it as the quantity is between negative A and A. That's the first case. And then we solve for whatever the quantity is. In the second case, where the absolute value quantity is greater than A or is greater than or equal to, then we write it as two separate inequalities and solve each. We'll get two separate intervals, usually, and we will describe those solution intervals in whatever notation our instructor would like us, either on the number line or set builder notation or interval notation. All right. If you have any questions, feel free to ask them in the comment section. I'm sure we check this stuff, or you can always ask your instructor or come to the TLC.